Hello friends, I'm Nikita and you are watching Prepare for GATE. Electronic devices. This subject contains 3 to 4 questions in GATE examination every year. The questions mostly could be given in comprehensive type questions where the question might seem a lot lengthy. However, a direct formula based question is often asked. Moving on, let's see the syllabus. Energy band diagram in intrinsic and extrinsic silicon. Carrier transport, diffusion current, drift current, mobility and resistivity. Generation and recombination of carriers. Poisson and continuity equation. PN junction, Zener diode, BJT, MOS capacitor, MOSFET, LED, photodiode and solar cell. Integrated circuit fabrication process, oxidation, diffusion, ion implantation, photolithography and twin process. The topic we are going to discuss is energy band in intrinsic and extrinsic silicon, carrier transport, generation and recombination of carriers, and Poisson and continuity equation. Energy band are the level of band formed when two different atoms comes in close approximation of each other. As the atoms are put together in a solid, various interaction among the atom will balance the proper interatomic spacing for the crystal. The linear combination of the individual atomic orbitals and also the formation of different energy level dependent on the number of atoms brought together. Pauli exclusion principle must be taken care while decoding the energy levels. You can see in this diagram that there are two atoms and whose outermost shell is being combined to give a separate two levels. One is conduction band and one is valence band separated by a band gap. From the given figure, let's assume that the two atoms have one as 6n states and 2n electrons. We can say that the 6n states means the valence shell is a 3 or p, you can say simply, and another having 2n states and 2n electrons. You can say that it is an S shell. In their outermost shell are brought together. When the distance between their states reaches the equilibrium interatomic spacing, these bands split into two, having an equivalent difference of energy known as Eg or forbidden gap. The formed band after splitting will be termed as valence and conduction band, having 8n state, 6n of former and 2n of later, combining to give 4n each. In silicon at 0 Kelvin, 4n electrons will be occupied by the formed valence band, that is the lowest energy band, and the conduction band will be completely empty of electrons and there will be no electrons in the forbidden gap. Metal, semiconductor and insulator. If we talk about metal, we say that the two bands, conduction band and the valence band, both overlap each other or both are partially filled. For semiconductor, valence band and empty conduction band, there is filled valence band and empty conduction band, and there is a gap of Eg, forbidden gap between both the levels. Insulator have high forbidden gap. The highest forbidden gap could be measured in diamond, direct and indirect semiconductor. If we further differentiate a semiconductor into two, direct and indirect, on the basis of light falling on the semiconductor, then we can say direct semiconductor is when an electron in conduction band can fall into the valence band, giving off the energy in the band gap, e.g., as photon of light. If an electron stable in conduction band gets an energy from the photon incident on that semiconductor, then absorbing that energy, it falls back to the valence band. It releases that amount of energy in the form of light. An electron in conduction band which drops to in the filled valence band can release its energy and falls to an intermediate energy level. That means that the electron on absorbing the photon energy, it doesn't fall back directly or at all to the valence band, because we know in silicon there are 4 electrons in the outermost shell. If you consider that already all the 4 valence band bonds are filled in terms of silicon, then there is no valence band is available or space is available in the valence band. Hence, the electron, rather than falling back to the valence band, it falls to some intermediate level between the two states, termed as an intermediate energy level. Intrinsic and extrinsic semiconductor. There are two types of semiconductor on basis of their purity. Intrinsic semiconductor is a pure semiconductor without any impurity. For example, silicon and germanium. They are also termed as non-degenerate semiconductors. Intrinsic semiconductors have 4 valence bands. Thus, all the 4 electrons take the place in the valence band and none is present in conduction band. Thus, at room temperature, the semiconductor is an insulator. Now, on basis of various impurities, as we already know, that intrinsic is a pure semiconductor and extrinsic is totally opposite to it. Extrinsic is a doped semiconductor. Dope means a mixed and an impurity is added to that semiconductor. Mostly impurities in the form of group 3 and group 5 present in our periodic table are added as dopants. And this whole process is known as doping. As group 3 electrons at group 3 metals have 3 electrons in their outermost shell, so they can accept 1 electron more. To form such type, they are termed as acceptors and added, and in group 5, such as phosphorus, they have an extra electron. Group 5 is a N type and group 3 will be a P type. A N type semiconductor having large concentration of electrons and P type having large concentration of holes. The dopant from group 5, having talked about N type and P type, let's discuss more about them. Doping from group 5 of periodic table induces electrons in the semiconductor. Doping from group 3 of the periodic table induces hole in the semiconductor. Energy level so formed contains the electron near to the conduction band, which is often said to be donor level. Energy level so formed contains the hole near to the valence band, which is said to be acceptor level. As you can see in the diagram below, that in the extra electron are present in the donor level, which are passed to the conduction band, having a imparting a small amount of energy, C minus ED, and add to the conduction band, that is increasing the amount of current. Now EA, acceptor level, is present near to the valence band. It can drop the electrons into the valence band, imparting further current. Now let's look at one of the question which happens to come in GATE 2017. It says that a bar of gallium arsenide is doped with silicon such that silicon atoms occupy gallium and arsenic site in the gallium arsenic crystals. Which one of the following statement is true? Silicon atom act as p-type dopant in arsenic and n-type dopant in gallium site. Yeah, silicon atom act as n-type dopant in arsenic and p-type dopant in gallium site. Silicon atom act as p-type dopant in arsenic as well as gallium, and silicon atom act as n-type in arsenic as well as in gallium. Now let's solve this question. You can see that gallium arsenide is combined of two element gallium, which is group 3, and arsenic of group 5. Now if we dope a gallium arsenide impurity in gallium arsenide bar, then if we compare these two groups having different belonging to different groups, then we cannot say that silicon act as n-type and p-type. Same, just like same in both the groups. This could not be possible. Now the difference lies between whether it acts as n-type in arsenic and p-type in gallium, or n-type in gallium or p-type in arsenic. If we see that the number of electrons present in silicon as compared to gallium is larger, that means a larger electrons present in silicon as compared to gallium. And we know that n-type semiconductors are those semiconductors which contains larger electrons in comparison to holes. Then we can easily say that silicon acts as p-type dopant in arsenic, having less number of holes, less number of electrons and large number of holes, because as comparison to arsenic, which already has a larger electrons, and in comparison to electrons it has less number of electrons and more number of holes. That's why it acts as p-type dopant, whereas in gallium it has larger number of electrons than gallium electrons. That's why it acts as n-type dopant. So answer A, that's our rightful answer. Oh, I have mentioned it over here. Okay, let's see